Let us now discuss torsion of structure components. Torsion refers to the twisting or rotational deformation of a structural element when subjected to torque or twisting moment. In other words, it is the result of a force that tends to rotate an object around an axis. In this presentation, we will consider deriving and applying the twisting and torsion moments onto circular shafts or closed thin wall tubes. We won't consider the twisting of non-circular shaft because that is a complex subject and that is related to advanced structural mechanics. We will start off our presentation with some assumptions based on which we will derive the well-known torsion formula and then try to solve problems using the torsion formula. So let us now assume a shaft which is cantilevered out. In other words, a shaft which is a circular shaft which is fixed at point O dash, and a torque of T is applied at point O. By torque, we mean moment applied about the longitudinal axis of the shaft. So the longitudinal axis in this picture is OO prime. As we discussed, we will confine ourselves to circular shafts, and based on that, the first assumption is circular section remains circular. In other words, when we apply torque onto a circular shaft, after deformation, all the cross section along the longitudinal axis will stay circular. So, in other words, we won't have any ovalization or deformity of the cross section. The cross section can move from one place to another, but it can't deform. So the cross section won't deform, it will stay as circular. However, it can move from one place to another. The second assumption is that plane section remain plane and do not warp. Plane section remain plane is a well-known assumption which we took in deriving the flexure formula also. The same applies over here. So the plane section remain plane says that a cross section which was plane, and in our case a circular plane section, that will stay plane after deformation. So in other words, the cross section won't warp. Warping refers to the deformation or twisting of an object out of its original shape. So in this figure, we can assume a channel section which is subjected to some torsional moment. And as a result of that torsional moment, the end stays fixed, but the rest of the section has deformed. The channel section, original cross section, has deformed, especially in this middle region. So we can see that the top flange has moved forward, and there is a reflection of this bottom flange which would have moved backwards. So that deformity in our derivation is not allowed. So in our circular shaft, we are saying that the circular cross section will stay as circular and there won't be any out of plane deformation of the circular cross section. The third assumption is that the projection upon a transverse section of a straight radial line in the section remain straight. So under the light of assumption number 3, if we have a line OB on any cross section, that line OB after application of torque might move to the position OC. However, it will stay straight. So OC can't result in a jagged line. It will stay straight as it was before. Its position might change, but the line stays straight. So in our figure, OBAO prime is actually an element. This element has got two sides on two cross sections, OB on the free end cross section and AO prime at the fixed end cross section. And there are two longitudinal sides of this element. One is AB, which is along the longitudinal axis, and one is O prime O, which is along the center of the shaft. And that's also along the longitudinal axis. Now, after deformation, the red element changes into a green element. In other words, AB, which was originally straight, would twist into a helical AC through an angle of a twist, which is called phi. But during this whole phenomena, we would have OB equal to OC. So OB hasn't expanded or squished, only its position has changed from OB to OC. Assumption number 4 is stating that the shaft is loaded by twisting couples in planes that are perpendicular to the axis of the shaft. So we have an applied torque at the cross section O, and as a result of this applied torque, we would have an opposite torque developing, or we can say a resisting torque developing at the cross section O prime. These two torques are perpendicular to the axis of the shaft. So if we assume a right hand rule, according to that, the thumb of the right hand will give us the direction of the moment if the finger curls are in the direction of the applied moment. So the outward drawn normal corresponding to the moment or corresponding to the thumb is in line with the axis of the shaft. If this thumb is inclined or having some inclination with the axis of the shaft, then the torsional formula will not be applicable. We can also say that the applied moment is perpendicular to the axis of the shaft. The fifth and the last assumption is that stresses do not exceed the proportional limit. So that means to say that we should always stay within the elastic limit. The torsional formula is only applicable in the elastic limit. Let us now proceed towards the derivation of the torsion formula. So we assume a cantilevered shaft which is subjected to some torque at the free end. In order to conceptually understand the phenomena, we will assume that the longitudinal shaft is discretized into small elements as shown. In other words, we draw circles and longitudinal grid lines on the shaft. Before application of the load, all these grids are in the form of small rectangles. Once we apply the torque, the circular grids will stay circular, whereas the longitudinal grids will twist into a helix. Please note, a helix is a three-dimensional shape of wire wound uniformly in a single layer around a circular object. We can imagine an example of a spiral staircase which looks like a helix. This second figure clearly shows that the circular grids are all parallel to each other, whereas the longitudinal grids have twisted. As per our assumption, the cross section at the end will stay plane and it wouldn't bulge out or in. In other words, it wouldn't warp. We define angle phi as the angle of a twist, also known as angle of rotation or twist angle, which measures the amount of rotation or twisting that occurs along the length of the shaft subjected to the torsional loading. It is important to note that radial lines located on the cross section at a distance x from O prime of the shaft will rotate through the twist angle phi of x. So we can imagine that a radial line at point O of the cross section has moved by an angle phi in such a way that point B has moved to point C. We can assume that the cross-section is made up of infinite fibers, which are in the form of concentric circles. Every concentric circle is at a distance rho from the point O. In order to make this further clear, we will isolate a small element which is located at a distance rho from the axis of the shaft O prime. Please notice that the angle of the twist changes as we move from O prime at the fixed end to point O at the free end. The angle of twist is 0 at the fixed end and changes almost linearly as we move towards point C. As we move towards point O, the maximum magnitude of twist angle is at the free end. Therefore, we take variation of the twist angle phi with respect to x, which is along O prime O. In other words, our x-axis is along O prime O. This is also shown in this figure where y and z axes define the cross section and x-axis is along the longitudinal axis. As we said, we isolate a small element located at a distance rho from the axis of the shaft. So cross-section wise, it is located somewhere in the middle between the axis and the extreme and which is the radius. We can see that due to the deformation stated over here, the back end and the front end of the element will undergo a rotation. The back face will have a rotation phi of x and the front end will undergo rotation phi of x plus delta phi. So we can say that the difference between the rotation is delta phi. This delta phi causes the element to undergo shear strain. We can also appreciate that from this deformed profile of our shaft, where we can see that before deformation, our longitudinal and radial grids were making 90-degree with each other. So every block had longitudinal and radial axes meeting orthogonally. After deformation, however, the edges of the element and the angle between them changes and the angle becomes less than 90-degree. Looking at our isolated element A, B, C, D, we can say that initially the angle between AC, which is along the radial grid, and AB, which is along the longitudinal grid, was 90-degree. After deformation, AB moved to point AD. In other words, point B moved to point D, resulting in an angle between AD and AC less than 90-degree. Thus, angle gamma would be equal to pi by 2 minus theta prime. Therefore, we can write gamma is equal to pi by 2 minus theta prime. As we discussed that BD is located at a distance phi from the axis of the shaft. So BD can be written as rho delta phi. Please remember, delta phi is the angle of the twist. Therefore, BD in the transverse direction is rho d delta phi, whereas BD in the longitudinal direction is equal to gamma delta x, where delta x is the length of our element. Delta x is along the x-axis as shown over here. We can take a limit, and in limit delta x will turn into dx and delta phi will turn into d phi, making the equation, the BD equation, equal to gamma is equal to rho d phi by dx. By doing so, we are introducing the concepts of calculus into our derivation. As we have discussed that no warping of the cross section is allowed, and also the radial lines will remain radial after deformation. Thus, the longitudinal fiber AB will deform into fiber AC. Thus, longitudinal fiber AB will twist into fiber AC, but it won't bulge out or bulge to the sides. Because of this type of deformation, we can say that our angle d phi, which is in the radial direction, and dx, which is in the longitudinal direction, their ratio will stay constant. So no matter which radial line we take, the ratio of d phi by dx will stay the same. From this equation, we can get gamma is equal to rho by c times gamma maximum. Plugging value in our well-known shear equation, tau is equal to g gamma, will give us g times rho by c gamma maximum, where g is the shear modulus and gamma is the shear strain. This tau or shear stress equation actually gives us the shear stress distribution over the cross section in terms of the radial position rho of the element. According to this equation, at rho is equal to 0, the shear is 0. And as we move away from the origin or from the axis, we start getting some shear stress in terms of rho of the element. At the extreme end or at rho is equal to the radius c, we would get the maximum shear stress. Thus, the variation of shear stress along the cross section from the axis till the extreme end is linear. We can also try to find out the entire torque produced by the element dA. So the torque produced by the element dA will be the shear stress time dA times the lever arm. So the element located at a distance rho from the axis has got the torque equal to shear stress time the area of the element time the lever arm, which is rho, and that has been done over here. Plugging the value of tau, we get rho time rho by c tau max dA. As we have discussed that tau max and tau are related to each other via ratio c by rho. So plugging the value of tau, we get rho by c tau max. Tau max by c is constant, so we can bring it out of integral. C is the constant radius and tau max is the constant shear stress for a particular cross section. So tau max by c is equal to rho square dA. The integral rho square dA is called polar moment of inertia. The polar moment of inertia describes the distribution of object's area with respect to an axis perpendicular to its plane. Please note that the polar moment of inertia is the shaft cross-sectional area about the longitudinal axis. In the case of flexure formula, The moment of inertia was the cross-sectional area of the beam about the neutral axis, which is x1. Thus, in the case of polar moment of inertia, that's the distribution of cross-section that the polar moment of inertia would be the distribution of this cross-section about the longitudinal axis, which is x3. So there is a difference between the polar moment of inertia and the moment of inertia used in flexure formula. The polar moment of inertia is symbolized as J. So tau max will be equal to T times C by J. Similarly, based on the proportionality of tau max and tau, we can write tau, which is the shear stress at any location rho from the axis of the shaft would be equal to T rho by J. The polar moment of inertia for the circular shaft can be determined using an area element in the form of a differential ring. Thus, this differential ring has got thickness equal to d rho and the circumference equal to 2 pi rho. This can be unwrapped and the area of this differential ring can be found as the circumference 2 pi rho times d rho. So if we unwrap this differential ring, we will get a rectangle having one side equal to 2 pi rho and the thickness equal to d rho. Plugging the values in our polar moment of inertia equation, we get polar moment of inertia equal to pi radius power 4 by 2. If we have a tubular shaft, in that case, our polar moment of inertia would be equal to pi by 2 outer radius power 4 minus inner radius power 4. Thus, now we have our torsional stress equation or the torsion formula equal to T rho by J. In order to find out the maximum torsional stress within the shaft, we have to check whether the torque T is the only torque applied on the shaft. If it's not, then we have to determine the point where we have the maximum torque applied and work out the torsional stress corresponding to that point. So this concept will become further clear when we discuss few examples. The first example is about a solid shaft of radius c, which is subjected to torque T as shown in this figure. We are asked to determine the fraction of torque that is resisted by the material contained within the outer region between C by 2 and C. So as we discussed that the whole cross section of the shaft can be considered as discretized into small elements and every element of this cross section is resisting the applied torque. In this question, we are asked that how much torque will be resisted by the material between C by 2 and C area. So in this case, first of all, we will have to determine the torque corresponding to the region between C by 2 and C. As we know, tau is equal to rho by C by into tau max. Thus, the torque d tau on a circular ring will be equal to rho times tau dA. dA will be equal to the circumference times d rho. So 2 pi rho is the circumference of this ring and times d rho will give us the area of this annular ring. That will be multiplied with rho by c tau max, which we got from this expression, tau is equal to rho by c tau max. And the first rho in this expression is the lever arm. For the entire shaded region, we will have to take an integral between c by 2 and c. So this whole expression will be integrated between C by 2 and C. Plugging the values, we get 15 pi by 32 tau max C cube. This is the torque resisted by the region between C by 2 and C. Now we have to get the torque corresponding to the maximum shear stress. So our torsional equation for tau max is Tc by J. So T times C and J is pi by 2 C power 4, which will give us tau max equal to 2T by pi C cube. Plugging the value of tau max in equation 1 will give us tau prime equal to 15 by 16 times T. So tau prime is actually the torque corresponding to the region C by 2 and C. That will give us about 94% of the torque. So that means to say that 94% of the torque is resisted between the region C by 2 and C. The rest is resisted by the region 0 and C by 2. Thus, as we move away from the axis of the shaft, that region will resist the maximum torque. All the annular circles which are away from the axis of the shaft will be resisting the bulk of applied torque. Let us now discuss another example where we have got a shaft subjected to different torques. As we said in whilst discussing the absolute maximum torsional stress, that we will have to work out the maximum torque within the shaft. We are asked to find out the shear stress developed at point A and point B located at section AA of the shaft. Point A is located at a distance 0.75 inches from the longitudinal axis of the shaft, whereas point B is located at 0.15 inches from the axis of the shaft. The shear stress corresponding to point A will be bigger than the shear stress corresponding to point B. So first of all, we will have to find out the moment at point A. So summation of moment about the x-axis must be equal to 0, which gives us 42.5 minus 30 minus t equal to 0. In this expression, we are considering moment in clockwise direction is 0. That will give us t equal to 12.5 kpinch. Once t is worked out, after that we will find the polar moment of inertia, which is pi r4 by 2. Then we will plug the values in the shear equation. At A, it is Tc by J, which is 0.75 inches, and we get 18.9 ksi. For point B, everything remains the same except the radius. Radius is 0.15 inches. Thus, we would get 3.77 ksi. As we discussed, the shear at A will be higher than the shear at B because point A is located furthest from the axis as compared to point B.